Welcome back to class. We're going to look into some of the health effects of climate change today, and we're going to begin with an examination of heat waves. And for those of you taking this class in Europe and who are around in Europe in 2003, you will likely remember the heat, especially if you were in Western Europe. This map shows the temperature anomaly over Europe in the summer of 2003. And if you look at this map, what it's showing you in red are the temperatures that were above average during the month of July in 2003, upwards of 10 degrees Celsius for large parts of southern France. These temperature anomalies are compared to 2001 in the summer. So you're looking at 10 degrees above the 2001 summer on average for a month. And that's quite warm. There were approximately 50,000 people who died in this heat wave. And those people died prematurely. So they're not people who would have died a few months later. If you look at the death records in Europe from this period of time, particularly in France, it's clear that there is an excess amount of mortality during that heat wave. There was also about 10% of the European crop lost during this heat wave. Some countries were much more affected than others. So heat is a major factor in both human health directly and through nutrition. We're going to talk about that in class today. Before we get into the details of that, I want to present a framework for you to think about how climate change affects health. And that's displayed here. This is not the ultimate model of how climate change affects health, but it is a model that I'm going to use in class, and I hope will be helpful to you in understanding the pathways through which climate change can affect health. It all starts with increased concentrations of greenhouse gases, like we've discussed. And from those, several things happen. One is there's increased energy in Earth's atmosphere. Now, I say increased energy in Earth's atmosphere rather than warming directly because that energy actually has several effects. And just so to make sure you remember, when I'm talking about the increased energy, I'm talking about the ability of greenhouse gases, as we discussed, to trap energy within Earth's atmosphere. So, if we have increased energy in Earth's atmosphere, that has three effects that are particularly relevant to health. These are not the only effects of that increased energy, but there are three. The first is warming, as we've discussed. The second is sea level rise. And the third is an increased incidence of floods and droughts, or what we call an intensification of the water cycle. But there's another set of pathways that are important to think about that have to do with elevations in CO2 alone, that are independent of this energy. So increased CO2 can affect allergenic plants. We're going to talk about that. It can affect crop nutrition and the ability to grow crops. And it has effects on the acidity of the world's oceans. Ocean acidification has been called the, quote, other CO2 problem, and it's one of great significance for our ability to lead healthy lives. So if we start with increased energy in Earth's atmosphere, I'm going to follow a few pathways. The three pathways I talked about are warming, floods and droughts, and sea level rise. These three things, either independently or in combination, have these health outcomes. These are not all the health outcomes, but they're the ones I'm going to focus on in class because I think they carry the greatest public health burden. Heart and lung disease, effects upon water quantity and quality, infectious disease, food security and nutrition, and mental health. I'm also going to make the case that there is a final common pathway to the increased energy in Earth's atmosphere that, as I mentioned, is due to the greenhouse gases we've added to the atmosphere, and that's population displacement. So all of these effects of climate change, all of these health effects that are caused by warming, floods and droughts, sea level rise, all ultimately funnel down into population displacement. And that, to me, is perhaps the single greatest public health concern related to climate change. If you want to find some of the most unhealthy people on Earth, be it because of infectious diseases, nutritional deficiencies, trauma, mental health, and so forth, you can look at people who have been displaced. refugee populations. So I think this is a critically important piece of the public health concern that surrounds climate change. A piece of that is that because of the effects of climate change on things like food and water and spread of infectious diseases, these create resource shortages that can increase chances of conflict. It's also true, as we'll talk about, that heat waves and warming in particular can be associated with increased conflict. And that, of course, plays into population displacement as well, and we'll touch upon that here. So this is the framework within which increased energy in the atmosphere has health effects, and we're going to talk about each of these in turn. To start with, I want to talk about heat stress and how it affects our hearts and lungs. So one of the questions you might ask is, if we've warmed by about 0.7 or 0.8 degrees Celsius, and we're looking at warming another several degrees, as this IPCC projection graph shows, how can a few degrees of warming Celsius have a significant effect upon the likelihood of heat stress and heat waves? After all, in Boston, where I am today, the temperature is going to probably vary by 10 to 15 degrees Celsius or more. And, how does that compare with just a few degrees of warming over the next century? So that's the first question I want to tackle. If you were to plot out the high temperature in Boston in the summer, let's say, on pick your favorite summer day, and you did that over a period of 100 years, and you plotted that on a graph where the temperature was on this axis, and every time you had a temperature of a certain measure, you put a point here and another point if it was the same, and then a couple years it would be a little bit cooler, and a couple years it would be a little bit warmer. And you put all those points, you would wind up with a distribution that looks something like a bell-shaped curve as is pictured here. Now in that bell-shaped curve, there'd be a relatively small proportion of years in which that summer day would fall into this tail of the curve, the very end of it. And the likelihood of having a heat wave would be out here in these extremely hot days. But what happens if you shift that curve, that whole distribution, if you shift the mean, the average, which is what we're talking about with these changes in global average temperature, over by a degree or two? Well, then instead of having this relatively small area here, you wind up having a much bigger area in blue here. So you increase this area a lot, but then you have this new area over here that doesn't really exist in the first curve, but is extremely hot. So this is just a graphic illustration of what can happen to temperatures through just a few degrees warming Celsius. So scientists have looked back at that heat wave in 2003 that was so severe in Europe and asked the question, how much has the addition of greenhouse gases since the Industrial Revolution affected the chances of having a heat wave that severe? And this paper, published many years ago now, said that it's likely that the summer of 2003 was the hottest in Europe at least since 1500. But more interestingly, they said that if you look at a threshold for mean summer temperature that was exceeded in 2003, but in no other year since the start of the instrumental record in 1851, they estimate with 90% confidence that the human influence has at least doubled the risk of such a heat wave. And again, think back to the graph of those distributions. If we've pushed the mean of those distributions over, you increase the chances of having heat waves like the one in Europe. There was other research done on that heat wave that's even more compelling about how the addition of greenhouse gases and the addition of energy to the atmosphere is affecting the climate of the planet that in turn has implications for heat waves. This is another paper from Nature in 2004. And in this paper, which was published in Switzerland, the authors used data from the summer, June, July, and August, and they did the same kind of plot as I showed you before, where they took the temperatures in these months over a long period of time from the, roughly 100 years of data, and they plotted each month's average temperature as a bar here, and you get a distribution. And then in this graph at the bottom, this is all 3 summer months, June, July, and August, put together, and you'll see this distribution. And 2003 is way, way out there. In fact, 2003 is what are known as 5 standard deviations above the mean. Now, standard deviation is a measure of the dispersion of the data, how spread out it is. So when you have a curve with a peak like this, the data is more tightly packed together, the standard deviation is smaller. When it's more distributed like this, the standard deviations are bigger. But given that distribution, 1 standard deviation is a certain distance away from the mean. 5 standard deviations is extremely unlikely. In fact, the probability of a summer being as warm as it was in 2003, given this data from Switzerland, was 1 in 2 million. So that the heat of 2003 is something that, given the historical distribution of temperatures, would occur once every 2 million years. And the authors, given that conclusion, said, this seems pretty unlikely that this summer was a 1 in 2 million year event. And they asked the question, perhaps the distribution of data is changing, that the spread of temperatures in the summer is changing as a result of the addition of greenhouse gases to the atmosphere. So they did a modeling study. So to start with, they did a control scenario, which is 1961 to 1990. And this is the distribution of temperatures. And you see that the curve is fairly short and tall because the data is fairly well compacted together. And then they did a regional climate model and found that, and out to 2070 to 2100, and found that the distribution of the temperatures was much broader, so that the curve is much flatter. And what that does is it makes extreme temperatures more likely. So you can see that the shifting of the curve, both pushing it down and shifting the mean over, increases the probability in the tail here. And then they just showed the same data on a map, and this is the change in temperature variability, with the largest areas here in Central Europe and then smaller percentages of change as you move outside of that. So just to recapitulate here for a second, if we shift the mean of a temperature distribution, we increase these record hot days and we very much increase hot weather. If you change the variance, you increase the spread of the data, you again increase the area in the tail, in the hot tail. And then if you shift both the mean and the variance, you see you get a very big increase in this hot tail. Now, it is true that when you shift the mean over, you get less cold deaths, and that will certainly be the case. But it seems that the distribution, just based upon what we're seeing here, is that there's still going to be some extremely cold times, but the increase in the extreme heat is going to be much, much greater than the loss in the cold. So how do people get sick in a heat wave? Well, there's temperature stress. The temperature causes people to lose water. They get dehydrated. And the combination of temperature stress and dehydration can lead to heat stroke. And heat stroke is not a vague term. It actually refers to a condition in which people are so overheated and so dry that they can suffer permanent neurological defects. Heat stress is essentially related to the body temperature going up so high that it damages organs and causes them to not work properly. As many of you know, the incidence of diabetes in the world is going up tremendously, and diabetics have a much harder time controlling their blood sugar when they're dehydrated and when the temperature goes up. Temperature also affects air pollution, and we're going to talk about that, particularly ozone. And ozone makes it very difficult for people with asthma and COPD. There's a higher incidence of asthma exacerbations, and people with chronic obstructive pulmonary disease, COPD, having trouble breathing. And air pollution can also be a trigger of heart attacks, which we'll talk about. So there are lots of pathways through which heat itself can promote problems for health. But interestingly, there's data that suggests that during heat waves, there are increased rates of accidents, suicides, and homicides. So again, that increased temperature may somehow fuel the potential for these kinds of health-related outcomes. So that's our introduction to heat waves and why heat waves and heat stress are going to be more likely as the climate warms because of the shifts in distribution. And next time we're going to look into some other pathways through which climate change and increased energy in Earth's atmosphere can affect health. I'll see you then.